Okay, so it's all working. Yeah, if there's any questions, please interrupt. Okay, so now the second part is going to be more storytelling. Okay, now it turns out that there's sort of amazing open problem. I mean, really interesting, I think at least, open problems related to these objects. Right, so you can now ask, right? You can now ask, for example, can we actually build? So let's look. Things are more interesting in the complex numbers. Like, can we build? Sorry, can we build? Or maybe that's not the right question. Yeah, let's say, can we build like ETFs with these square vectors in CD? Right? In particular, notice that you get equality in the Welsh round. So what does that mean? It means that the value, right, of this is n minus d over d n minus 1, right? So for d looking like n squared, this is basically 1 over root d, right? So we're going to get coherence that's very small. Okay, this is a bit of an aside. So it turns out that these are important objects. So ETFs with these square vectors in CD, turns out that these are very important objects in quantum mechanics. Okay, they have to do with measurements. So these are, turns out, important in quantum mechanics. Okay, and they are called SIG POVMs. Okay, I mean, this is more storytelling, you know. Right? Turns out we do not know for which, if they exist for all dimensions. Okay? So it is an open problem. It is a conjecture known as Zauner's conjecture. Okay, so this is a relatively famous conjecture. Right? Make this small. So Zauner's conjecture states that these ETFs, or maximal ETFs, right, in this sense, or maybe let me write. So Zauner's conjecture states that. Oh, okay, maybe let me write it this way. Zauner's conjecture, which is open, these exist in all dimensions. Okay, this is an open problem in quantum mechanics. I mean, and in this area of sort of signal processing and so on. Okay, we do not know if this is the case or not. There's many constructions. There are many constructions for many dimensions, and there's infinite families, things like this. But we actually don't know if they exist for all dimensions. Okay, and once in a while, a new construction shows up, maybe done by computer or something. But there's still a lot that we don't know. Now, there are, however, things that we can do with low coherence or relatively low coherence. Let me just give you an example. So doing these actual constructions uses a lot of either combinatorics or sometimes some number theory and things of this style. And so this is a bit outside of the scope of the course, right? What I want here is to give you a feel for how one can actually exploit parsimony, right? Still recover vectors even though they're sparse. And what we need is basically that the matrix, right, satisfies certain properties. Your measurement matrix satisfies certain properties, right? Here, the columns shouldn't be they should be almost orthogonal, right? And in matrix completion will be also something of this style, and we will get there in a bit. But we can actually build a matrix with very low coherence. Okay, so let's look at an example. Okay, I assume all of you have seen the discrete Fourier transform. All right, so let's take F, the discrete Fourier transform. Okay, so what is F is a matrix, right? So it's a D by D self-adjoint matrix. Okay, let me just say so the D by D matrix. right? Right? And in CD, right? Okay, maybe I should have just said it's in CD. Okay, and it's just given by F is the matrix that gives the discrete Fourier transform, right? So it's 1 over root D, and then you have a bunch of ones, and then you have W is omega, omega square, omega cube, all the way to omega D minus 1, right? And now basically you have this squared, omega 4, omega 6, and so on and so forth, right? Omega 3, now, right, 6, and so on and so forth, right? Where omega is the root of unity, right? So omega is equal to exponential of minus 2 pi I over D. Okay, so we can write the entries of F. I mean, I'm sure you've seen this object before, but right, okay, I can't use, right, if I'm using I as the number, right, so I square equals minus 1, right? This is the I from the complex numbers I, not the I as in the index. So here I should use K and L, right? Then this is exponential of, right, minus 2 pi I, okay? And now I get this to a power, right? So over D, and it's W to the power, right? K minus 1 times L minus 1. Right, and naturally, because of the 2 pi, this is all modulo D. Okay, so in particular, all these entries have modulos 1, right, because they're root of unity to some power. And so now take the matrix phi equals an identity and the Fourier transform. Okay, so this matrix is D by 2D, right? The worst case coherence for it, right, it's easy to see. The worst case coherence is 1 over root D, right? If I take two columns, they are in the same basis, right? So this is an orthonormal basis. This is also an orthonormal basis. Right? So if I take two elements in the same basis, the inner product is 0. Okay? If I take the inner product between one element of the canonical basis and one element of F and one column of F, what do I get? I just get one of these entries, right? But these entries have norm 1 divided by root t, they have norm root t. Okay? So in particular here, we can get already the sort of 1 over root d coherence that we expect. And it's possible to build these objects much, much bigger. Okay, so in this course, we're not going to do that because that's not the intent of the course, but I give in the lecture notes links to, there's even this living document as in an archive paper that keeps getting updated with constructions of various equivalent frames and frames with low coherence and so on. Okay, but in particular, I should say that the theorem, right, the theorem from last week, right, already guarantees that for this phi, right, guarantees that for this phi, right, we can do, so L1 minimization recovers sparse vectors for, or as long as, right, as long as S is smaller than 1/2, 1 plus 1 over the coherence, but the coherence is root t, right? So something like on the order of 1/2 square root t. So as long as the sparsity is smaller than square root of the dimension, you get a savings of half the measurements. Now you only need to take half the measurements. Okay? It is actually possible to do much, much better than this. Okay? With constructions, there are constructions for much higher redundancy, right? So instead of being, right, this matrix was, D by 2D, right? You can do constructions with much higher redundancy, right? But I don't want to talk a lot about building these matrices. What you will see in towards the end of the class. So there are a couple of things that I wanted to still go over, but because I don't want to use tools or heavy machine, I mean, not that heavy, but machinery from probability theory, we're not going to do it yet. But in the second part of the course, you're going to see a lot more probability theory, and then I'm going to make it a homework in the end of the course to show this, because by that point, you'll have all the tools to do it, and it'll be a lot easier. Okay, so I'm going to call this end of the course homework. I think in the lecture notes I wrote it, I called it exploratory challenge. If we build phi by simply taking independent random columns, then with high probability, the coherence will be, roughly of the order of some logarithmic factor in n. Let me not specify for now what it is. You'll actually compute it, right? Think like log of n over square root d. So even random columns do quite well. And in particular, it means that we're going to be able to do sparsity levels, right, that look roughly like square root d over logarithmic factors in n, right? So you're going to be able to allow, this is going to give, via that theorem, s to be smaller or equal than basically, right, up to constants, square root d over polylog n. Right? So even if n gets very, very large, right, the dependency on n becomes only logarithmic on the ambient dimension, right? And this is what's remarkable. Okay, now there's many stories I would like to tell you, but unfortunately we don't have an infinite amount of time. So on this end, there's quite a few nice stories. One is that it turns out, okay, so now I'll be a bit vague because I mean, now we're in the storytelling phase of, I'm not going to show much math. So it turns out that one can remove this square root d. Okay, so it turns out it's possible. It's possible to do reconstruction basically for s being something like d over log n. Right? Another way to think about this, right, is that the number of measurements d, right? Another way to think about this, maybe that makes more sense, right? Another way to think about this is that d, which is number of measurements, right? Because it's the number of rows in the matrix, okay? Just needs to be bigger or equal than s times log of n. Right? So besides this logarithmic factor of n, the number of measurements we need is just the sparsity level of our object we want to recover and not actually the underlying dimension of the object. Okay? However, we have no idea how to do this with deterministic constructions. So with the random construction, as you see here, okay, I explained this a bit better in the lecture notes with links in case you want to study more about this. And if you want to talk about this, I mean, let me know. If you'll stop by my office hours, I'm happy to chat about all of this. So as you'll see towards the end of the course, if you just take random columns, they have very low coherence already. But actually, there's more than that. As a matrix for sparse recovery, they're actually going to do a lot better. Although proving that is outside of the scope of the course, because it requires some random matrix theory. But the really interesting thing is that we have no idea how to do this with deterministic constructions. Random constructions work up to this level, right? Rather than here, you would get something like d being s square log n or s square log square n or something like that. We have no idea how to build these matrices. So we know random matrices work with high probability, and we have no idea how to break what's called the square root bottleneck. And there's many, many open problems. Another open problem that I can mention in this field, like in this, the field of in this understanding sparse recovery and these objects such as packings and so on, is that what we did here, and again I give references in the lecture notes, is what I did here, right? So this construction here, what was the trick? I came up with two orthonormal bases such that the inner product between every pair of vectors is of size 1 over root d. Okay? So now I can define the following object. Okay? Two orthonormal bases are said to be mutually unbiased, right? I can have now a definition, right? Two orthonormal bases, say V1 through VD and U1 through UD, right, in CD, right, are mutually unbiased bases. Let me use this. If and only if, for all I and j, the inner product of ui with vj is 1 over root d. Okay? If you sit down for 10 minutes, you'll convince yourself that you can never ask for something smaller. Okay, by Parseval. I'm not going to do that here. Okay. And now, many bases. So K bases, orthonormal bases, right? Orthonormal bases are called mutually unbiased bases if they are pairwise, right? They are pairwise, mutually unbiased. Okay. If you like to think about open problems, here's an open problem. Okay, it's an open problem. I write it in red. We have no idea how many mutually unbiased bases can one build or exist, as in at the same time, in 6 dimensions. I mean, think about this. It's not, some dependency as things go to, it's 6. That's it. Like you're in 6 dimensions. This is a simple definition about unitary matrices, right? We have no idea. We know that the best, so world records. So we know that it's smaller or equal than 7. In fact, we know that for any dimension d, it's smaller or equal than d plus 1. And this is tight when it's a prime power. The construction uses the fact that it's a prime power. And it's big or equal, I think, 3 is the best known. We have no idea. And this is again an object that's important in quantum mechanics. Okay, so the lesson here is parsimony can be exploited, right? Sparse vectors can be recovered with less measurements than the dimension, right? We did that explicitly. We actually were able to show that for this case. And through the homework, when you have a few more tools in probability theory, you will show it here. Right? To actually try to build objects that allow for this deterministically seems very, very hard and gives rise to all these interesting open problems. Okay? And random constructions will work very, very easily, as you'll see. Okay? So now in the last 25 minutes, I want to tell you a little bit about matrix completion. Okay? So unfortunately, I couldn't find, there doesn't seem to exist satisfactory enough deterministic theory for matrix completion. And so I'm not going to be able to show many theorems about it. I can now, however, with the math we developed for sparsity, I can motivate the theorems that are used for matrix completion, and you'll be convinced that they are natural theorems, that they are natural algorithms. To prove the theorems that those algorithms work in matrix completion, we really need heavy machinery from probability theory, a lot of duality, some random matrix, and so on, which I do in the master's course I teach, but here would be too much. But the core ideas behind the algorithms are sort of all present in a way. Besides the machinery, they're all present in these examples, and that's why we spend so much time studying the sparse recovery. Okay, so let's talk about a bit about matrix completion. Okay, so the problem, this is important in recommendation systems. Okay, so the idea, so this became famous in part because of something called the Netflix prize. I don't know if all of you have heard of this. So, I mean, I could talk for hours about the Netflix prize. However, what I recommend, so I wrote a few links on the lecture notes. You should take a look at those links because there's like, actual press coverage of the Netflix prize. But basically what happened is I think maybe sometime in 2006 maybe or 7 around there, Netflix launched a contest in which the idea was to improve, the goal was to improve their recommendation algorithms for movies. Okay, so people rate their movies and then Netflix tells them what movies they think they're going to like. And so they wanted to improve this. And so they made a challenge to the whole world that they would give part of their data, right? And then you would have to come up with a recommendation algorithm. And whoever did the best would get $1 million. So this ran for maybe 4 or 5 years, the contest. So there were like at the end of each year, there were partial prizes and things like this. And it was sort of just an amazing experience in, it's extremely interesting to go and read the stories around all of this, each person, the competitors, what they were trying to do and so on. And there's all sorts of amazing stories of how the teams that started winning, what happened is the teams that started doing well, they started combining algorithms and combining teams, right, and doing ensembles of algorithms and ensembles of estimators and so on, and they started doing well, extremely well, right? And then basically the way it worked is they gave you the data to play with. And then at the end of I don't remember what was the frequency, but let's say at the end of every month, they would allow you to test your algorithm on data that you have not seen, right? That they had more data. They didn't give you all the data. And then you could test your algorithm on data you haven't seen, right? Like the train test type of thing in machine learning that you'll hear a lot about in supervised learning, right? But it also makes sense in like things like recommendation system. And then the score was being kept of how different teams were doing in that sense. And then, if I'm not mistaken, and then the actual prize was going to be given not in that test data where people had tested algorithms. Let's say at the end of every month you could test it once, but on a new data set that had never, on a new data points that had never been seen before, right? Because there's this phenomena in machine learning that you might actually train to the test set. If you check very often if your algorithm is doing well in the test set, you might, without warning, be testing on the data set, be training on the test data set. Right? And so this was a case in which one team was like slightly above the other one. And I think when they tried on the very last data set, the team that was slightly below actually got up and won the award. And if you see, like I put the links in the lecture notes, and you can see the scores, the algorithms, and all this. And the scores are, I don't think even the decimal places that they show, I think they're just the same. I mean, it's kind of incredible. And the whole story and so on. I mean, I don't want to just talk about this, otherwise we would definitely get to the end and just talk about this. But go explore this because it's and to sort of see how much of a phenomenon this was. If you go to say Wired, for example, the magazine, you know it's not only that you see one article at the end of all of this. You see articles throughout the prize, like talking about the progress of different teams and so on. So it was really a big deal, right? And so what was the goal? Let me be a bit more precise, right? So there were users and movies, right? And then each user would rate a movie, right? Maybe you would rate, let's say, so the ratings were from 1 to 5, but let's say just plus or minus ones, just to make it, because I think that's probably now how it is actually. So they liked it or they didn't like it, right? So thumbs up or thumbs down, okay? Right, and you had many of these, and so on. right? So many users rated many movies. And the question, can we recover? I mean, recover versus predict, right? The ratings, I mean, we use recovery in sort of the more signal processing language, but of course you're not recovering anything because the people haven't watched the movies, right? The ratings of unseen movies, of unseen movie user pairs. And of course, I'm using plus or minus ones, but you could ask this question with any kind of rating. And so one key idea, so a key idea or observation is that this matrix, let's call it M is low rank or approximately. Let's say for the sake of argument that the rank of M is smaller or equal than S. Okay. And so now the matrix completion problem is, can we recover a low rank matrix M from observing some of its entries? Okay, this is very similar to the question of, can we recover a sparse vector from observing some linear measurements of it, right? Similar to sparse recovery. In fact, many of the ideas will apply. Okay, so the actual algorithms that won, they were ensembles of many complicated algorithms, like, or maybe no, maybe not necessarily complicated, but ensembles of different algorithms, right? There were basically different teams that try to exploit different things. Like, I read that there were some teams that realized that people rated differently if they were watching the movie on Monday or on a Friday, and or that people rated differently if they, if someone rated a lot of movies all at the same time, like 20 movies in the same sitting, then this meant that probably these were movies that this person had seen before, and was not just like they have just finished watching the movie and they rated it, right? And apparently they even used information like this. So there's certain, they give the example in one of the things I read that there's certain movies that how you feel about them right after you watch them or later is different. They say snakes on the plane doesn't sound as good a few days after you watch it. I would disagree, but and and uh, and and so these are effects that are not present on this matrix alone, right? So there's a lot more that you can do, but already just looking at this matrix and thinking of it as low rank, you can already do quite well. Okay, and so the central questions here is, how many entries do we need, right? Do random entries work? Right? Is it okay if all I get is random entries? That's what I mean by work, right? See the analogy with the theorems of D being bigger or equal than something. See the analogies of random vectors and low coherence. These analogies are real. What algorithms work? Okay, so let's talk a bit about this question, because I'm not going to be able in this class to prove to you that an algorithm works. I'm going to be able to answer a version of this question. Again, I'm going to answer it through homework for later in the course, but nonetheless, we can do it that way. Okay. The problem is that it's incredibly hard to come up with a good, satisfactory deterministic theory for this. Okay? Randomness appears to really be needed. If you really want to be able to recover from very few entries, if you just want to recover from, say, like 90 or 80% of the entries, then it's very easy, but it's not really that interesting. Okay, so what algorithms work? So I would say that we have, from our class, right, from what we saw in this first half of the class, there's two algorithms that arise very naturally. And in fact, one algorithm arises from the first half of this half of the course, and the other algorithm from the second. So here's algorithms that seem reasonable, although we will not be able to understand them, like actually prove mathematically that they work. So one algorithm is truncated SVD. So what I mean by truncated SVD, this is kind of a cool algorithm. So you basically do the following. You pick your matrix, take your matrix, take your matrix M. Okay, and let's say fill what you don't know with zeros, say. Okay, just for the sake of argument now. And now do the following steps. A, do truncated SVD. Right, so you're going to get another matrix M that is a little bit smaller. Sorry, whose rank is smaller. And you can do like truncated that you actually put the singular values to zero, or you can do some kind of what's called soft thresholding, where you just make the singular value smaller. Okay, there's all sorts of variants of this, but you can just say truncated SVD in the way that we talked about in the beginning of the course. Right? You just take the singular values, clip them at some point, set the rest all to zero. Now this matrix, right, observation, this matrix no longer agrees with the observed entries, right? You messed it up in the spectrum and so on. Who knows what happened to the entries? No longer agrees on observed entries. Right? I mean, it might, but it would be a miracle, right? Why would it? So what you do is you fix the observed entries. Right? So set the entries that are observed to actually their value that you observe them. Right? Set them to the observation. Okay? What is the issue now? You now change the entries. Who knows if this is low rank or not? Might not be low rank anymore. Right? Does everyone agree with this? So I grab my matrix, I set to zeros, the entries I don't know. Now I take a truncated SVD. Now the whole thing changed, including the entries that were observed. So I know I go and I change the entries that are observed back to what I know they should be. But now the whole SVD changed, so maybe now it's no longer low rank. Right? And so now, of course, I just repeat. Right? So I'll do alternate between A and B until convergence, or until convergence, say, or until one is happy with the solution, until we have a good solution. Right? I'm not being very precise because actually you would implement there's lots of different variants of this. This works pretty well. Okay. So this comes motivated from the first half of the course. Now is an algorithm that comes motivated from the second half of the course. The second half of the first half of the course. Okay. Second quarter. Okay, any questions about that algorithm? Right, this is what's called an alternating, alternating optimization, alternating truncated SVD. This has a few different names. Okay, if not, then I'll describe the second. I'll describe the second algorithm. So maybe I'll give you a second to think about what would the second algorithm look like. So it has to do with this, right, with the compressed sensing and sparse recovery. Right, so what do we know? Right, we know that the vector of singular values is a sparse vector. Right, this is the same thing as saying that it's low rank. Right, the vector, I mean, I could think of this as the vector of singular values is sparse. Right? So what does the whole sparse recovery stuff suggests? Right? Like the things above, right? The results above, the theorems above, suggest that what we should do is we should minimize, right? Overall, we should minimize the L1 norm of the vector of singular values, right? Such that, M agrees in the observed entries. Entries, sorry. Right? This is exactly what the stuff that we saw above, that L1 norm is a good way to impose sparsity, suggests exactly this. Right? But actually we have a name for this, right? This is minimum of the Shannon 1 norm. Right? The Shannon 1 norm is exactly the L1 norm of the singular values. Right? Such that, I keep writing M agrees with the observed entries. This is, of course, linear constraints, right? Because for the ij's that you know what it is, you just set mij equals to the observation. Agrees with observed entries. Right? These are constraints of the type, right? Mij equals yij for some ij's. Right? They're linear constraints. Right? So this is called nuclear norm minimization. Right, so the Shetton 1 norm has another name in this literature. It's called nuclear norm minimization. And turns out this is an extremely good algorithm for this problem. Okay, so I will not be able to prove that this recovers, right? So we will not prove here that, let me call this, let's call it Shetton 1 norm minimization, right? That S1 recovers low rank matrices. In many cases, so this will not be able to show in this course, but I show this in my master's course, and I mean I'll give references for how to prove this, but it definitely uses a lot more machinery. But the number of measurements needed will be something like you should expect roughly. Okay, I'm now going to be hand wavy, but a bit like before, you're going to expect that the number of measurements, the number of entries, in many cases, right? So provided that, there won't be there's also a notion of coherence, right? Somehow you have to get measurements from all the users and all the movies somewhat evenly and so on and so forth. But roughly the number of entries will look like the number of degrees of freedom of the problem, right? So something like R, the rank, times n plus m, right? Instead of m times n, right, for a matrix that is n by m. Okay, which is roughly the number of degrees of freedom. Okay, for some, I mean, for some matrices M, right? For, I should say, for some, yeah, let me not get much into this. I can just convince you that it won't work for all matrices M. If my matrix M is just a 1 somewhere and everything else is 0, this is, of course, a very low rank matrix, but if I just see a few entries, if I miss the 1, I'll never be able to do anything. It looks just like the 0 matrix. So somehow that's why it's difficult to come up with a deterministic theory for this. You have to rule out these matrices and you have to rule out the fact that you don't see maybe things like this. And so there's a lot more that goes into it. But basically, this whole stuff from before of sparse recovery and so on motivates these algorithms. I mean, the alternating, the truncated SVD motivates this algorithm, right? And right, maybe I should say for some matrices. Right, there's a notion of coherence that they need to satisfy. Okay, and the L1 minimization suggests this nuclear norm minimization. Okay? Now there's of course many questions, right? One is, well, can I actually solve nuclear norm minimization, right? I had to convince you that L1 minimization was a linear program. So it turns out that this is a semi-definite program. Okay, and turns out that one can solve, semi-definite programs efficiently, right? Even though this is not obvious at all, but turns out that you can solve this. I should say it's an STP. Okay, and so can be solved efficiently, even though this is not clear at all at this point. And what I'm going to do as sort of a homework for later, what we're going to see, so as homework for later, as homework for end of course, again, it's not that it's complicated, but it uses some tools from probability theory that I think it's best if you do this homework towards the end of the course. Right, this was the compromise that I got to in trying not to use probability for explaining this. Right, for R equals 1, so if the rank is 1, right, so let's say M is just equal to U V transpose, let's say the VLs, okay, and say and U and V have no zeros, it's not so hard to convince yourself that if you look at the entries that you observe, right, so these are the observed entries, it's not so hard to see that it's possible, like recovery is possible. This you can already think about now. Basically, if the graph, I mean, in particular, bipartite graph, whose edges correspond to observed entries, is connected. Okay. Where this adjacency, by where I think of this as an adjacency matrix, but here I think, right, I have, say, n nodes on this side, right, n nodes, m nodes. I do connections like this. There's no connections in between, and then I do my adjacency matrix, right? If this is an I and this is a J, then this would be mean the entry IJ is equal to 1. Okay? And so what we're going to do in the homework is for random dispositions, you're going to understand when is it that this graph is connected, right? So we'll see that for random observations, This will be connected, right? So graph will be connected. Basically, more or less, when okay, again, I'm going to be somewhat vague for now. In the homework, I'll be a lot more clear. Number of entries will roughly have to be something like, n plus m times the logarithm of this, right? And in fact, up here, I mean, all of this is up to logarithms, right? There's usually logs of things, okay? Say n plus m and so on. I don't, yeah, by here I mean up to logs. There's usually log terms in front. Let me just write polylog to, okay. Okay, and so you'll prove this, which is actually also a very, very nice result in random graphs. But already here, you probably are noticing that, right? We saw that connectivity has something to do with the eigenvalues of the adjacency matrix, right? Even though, I mean, this adjacency matrix is a bit different, right? And so the graph here is going to be random, so it has something to do with eigenvalues from a matrix that's random, right? And so understanding when matrix completion is possible or not has something to do with eigenvalues of a matrix whose entries are random, right? And this is why random matrix shows up so much. Okay, but we really can't, I mean, we don't have the option of getting into that, but this should already give you sort of a taste of how these things come into play. And then I'll give you a few references in the notes if you want to explore any of this, or I'm happy to chat and I can stick around and talk more. Okay, but so the goal of this, this last part was just more to try to show you how these things then in which directions do they go and how they all connect and so on. Okay, thanks so much, and I'll yeah, hope you have a good break. Sorry for taking 3 extra minutes, and then after the break we start with supervised learning. So Nikita is going to start with supervised learning, and then it's going to be half of supervised learning and then half, well, maybe a bit more than half, and then some online learning afterwards. Okay, so I'm going to stop the recording, and I'm happy to answer any questions or chat about any of this.